Okay, well, welcome everyone to this week's GBO Community Zoom. My name is Tony Ramajan. I'm the interim director here at the Green Bank Observatory. And what we like to do with these community Zooms is just go ahead and give you a brief introduction of what's going on at this in and around the site. So if you've joined these before, you will have heard that we have started our 10-year infrastructure plan and maintenance of the Green Bank telescope. And we are proud to say that we are now done with sandblasting the upper feed arm. We are now all set up for painting. So the folks out there have actually started priming and painting the upper feed arm of the GBT. Next up, in about 3 or 4 weeks, we're going to be replacing 5 wheels on the GBT. So that means we're going to jack up the GBT and replace 5 wheels along the azimuth ring. And then just to let everyone know that we're going to starting up observing sometime around the end of September. So if you still need to get those projects or set up, please contact your project friend, get in touch with us here at the observatory so we can make sure you're ready to roll starting at the end of September. In about 3 hours and 58 minutes is the NRAO GBO proposal deadline. So, after we listen to the talk today, everyone go back to writing their proposals and get them in before the end of the business day today at 5 p.m. Eastern Time. And with all the great data that we're collecting here at the GBT and delivering to you as PIs, if you have a really great result, you have a really great set of data that you want to show off, come and visit us at the AAS meeting. We'll be there in Arizona and Phoenix this January, and contact our press office. Our press office is always looking for new and interesting results that are coming off the GBT or any instrument on the Green Bank site, and be happy to put a press release together and get you advertised out into the scientific community. So those are the updates from the Green Bank site and the Green Bank Observatory here. And I'm very happy now to introduce our speaker today, Jay Lockman, who is he's a emeritus astronomer here at the Green Bank Observatory. He has celebrated over 50 years in Green Bank, and he is a world-leading expert on the gas inside the Fermi bubble wind. And so Jay today is going to talk to us a little bit about his work on the kinematics of neutral gas in the Fermi bubble wind. So please take it away, Jay.
Thank you, Tony. Uh, I'm sharing now. Okay, can you see that?
Yes.
All right. Um, very good. Yeah, thanks. I'm sorry, Keynote is asking. Okay. I'm going to be reporting today on the latest results of a long project that's been going on for more than a decade now on telescopes around the world. And that's about the contents of the Fermi bubbles. The Fermi bubbles shown here in an artist's conception are large regions filled with very hot gas, certainly several million degrees, emanating from the center of the Milky Way and extending up many tens of degrees above and below the galactic plane. Large galaxies like the Milky Way typically have things like this, which are driven either by AGN activity in the center of the Milky Way or by star formation. We really don't know, in the case of the Milky Way, what's driving the Fermi bubbles. But with the instruments that we have, and in particular the GBT, we're able to study gas entrained in the Fermi bubbles in a way that we just can't in other systems. So I'm reporting today on a new survey. First, let me show you the outline of the Fermi bubbles here. What we see in gray is the neutral hydrogen associated with the Milky Way disk, and on top of it in green and blue, a model for the X-ray emission from the Fermi bubbles from Miller and Bregman in 2016. And this is going to be the fiducial model I'll use throughout the talk. Also on here, we have the superposition of the hydrogen and the Fermi bubble outline. And you can see that the Fermi bubbles in the Milky Way encompass a region that is fairly devoid of H1, except at low latitudes. The survey I'm talking about today is shown overlaid on this map to the left. It's a region of about 500 square degrees mapped with the GBT and includes some previously published data. We cover almost -600 to +600 kilometers a second. And today, it's a very rich data set. One could approach the data from many different angles. But today, I'm just going to be looking specifically at the kinematic extremes, looking only at clouds, hydrogen clouds detected with the GBT that have a velocity with respect to the LSR of more than 130 kilometers a second. It's a somewhat arbitrary cutoff, but this gives us 220 clouds for which to study the kinematics of the Fermi bubbles. This is a sample of the velocity slice from the recent survey. You see, we go from about 348 degrees to about 16 or 17 degrees in the north, and a bit smaller coverage of that below the galactic plane. This is a slice at minus 126 kilometers a second. So actually, these clouds here will not be included in the sample I'm looking at today. Let me start by stressing how strange the population of Fermi bubble H1 clouds is. What we've got here is a slice through the galactic plane, parallel to the galactic plane, about 5 degrees latitude, about 20 degrees in longitude. And we go from longitude about 13 up to 35 degrees here. And the gray that you see in the center is the hydrogen normally rotating with the Milky Way. This is the data over some of the most intense star formation regions in the galactic disk. But you see that the hydrogen emission is pretty well confined within 100 degrees of zero LSR. On top of it, we have a sample in little red dots of some of the clouds that we observe in the Fermi bubbles. And you see they have such extreme velocities. Velocities like these are just not found in other places of the Milky Way disk. These velocities are extreme even when compared to some of the high velocity phenomenon that we know about in the center of the Milky Way. The grayscale here is an integration of the hydrogen emission over 2 degrees of the galactic plane. And you can see many features, the 3 kiloparsec arm, features that are all understandable as the response of gas to the potential, a bar-like potential, streaming motions in the center of the Milky Way. Superimposed on this in colors are samples of the Fermi bubble clouds. So you see that there's really no relationship between what's happening away from the galactic plane in the Fermi bubbles and what's happening below. Here's the description of the sample. The velocities go from more than minus 300 kilometers a second to greater than 400 kilometers a second on the positive side. And that part that's notched out in the center shows data that we're just not going to be considering today. The highest velocity clouds, more than 400 kilometers a second, as LSR velocity, are approaching the escape velocity from the Milky Way in this direction. So it's really an extraordinary population. This shows the sample in longitude and latitude, color-coded by velocity. The green dashed outlines indicate very roughly the survey boundaries. And you can see that clouds pretty much fill all available survey space. I want to draw your attention to the two open diamonds, one around 11 degrees and the other around 1 or 2 degrees. These are the sites of UV spectroscopy with the Hubble Space Telescope on, in the case of below the plane, a very distant star. In the case of the triangle above the plane, an AGN. And so these spectra are probing highly ionized, in many cases, very highly ionized gas along these lines of sight through the entire Fermi bubble. We just don't have H1 emission at a lot of the velocities that are shown, that show up in the ultraviolet. But I will stress the fact that we are sampling the same phenomena in both the ultraviolet and the 21 centimeter emission. So the clouds fill the observed region. I'll get into more detail in that in a bit. Now here's the geometry that we're dealing with. And I would just want to explain and make everyone appreciate how extraordinary the Fermi bubbles are. They are enormous. And so if we are looking at plus 15 degrees or minus 9 degrees latitude, the sun is on the left. And this is a projection looking at longitude 0. distance from the galactic plane vertically, distance from the sun horizontally, and the outline of the Fermi bubbles is there. They're just so enormous that along these sight lines, we really are probing very different regions, potentially of distance from the galactic center, distance from the galactic plane, location within the Fermi bubbles, and so on. And while this can be somewhat confounding, it also gives us quite a lever arm in understanding and analyzing what we see. First of all, what we measure is the LSR velocity. And in this case, my arrow is showing up the positive LSR velocities. But if we have expansion along these lines indicated by V rho, which is the expansion from the galactic center radially, we can see that as we march from the sun, first of all, we'll get projecting negative VLSR, negative velocities. Then it'll go to zero when the expansion is tangent to the line of sight, and then a long region where we'll get positive velocities. So we know right away if we see negative velocities in this model, we're on this side of the tangent point, positive velocities over here. And the LSR velocity that we measure is the projection of the expansion velocity times this cosine beta, the projection factor. Here's an example of cosine beta along the line of sight, distance from the sun for 3 different latitudes, 3, 6, and 9 degrees. And you can see that the projection factor is quite large. Namely, we're seeing a good fraction of the expansion velocity on the near and far sides of the Fermi bubble walls. And then it goes through zero over a smaller region tangent to the line of sight. The maximum projection is always at the Fermi bubble walls. This is data now. And here we're showing the latitude and the V velocity measured for this sample of clouds, along with in black diamonds, the ultraviolet results. And you can see basically that the UV spectra span about a similar range as the H1. There's no particularly difference in the kinematics, but that the kinematics of the positive velocity clouds is substantially different than the kinematics of the negative velocity clouds. Here, the negative velocity clouds are mostly confined within 300 kilometers a second of zero. The positive velocity clouds go well up over 400 kilometers a second. Also, we see negative velocity clouds to the survey limit, and we do not see positive velocity clouds to the survey limit. So here are my initial conclusions. The UV data are consistent with the H1 kinematics in broad outline. Positive velocities are greater in magnitude than negative velocities of this cloud sample, and we see no H1 clouds detected at positive velocities above a latitude of 10.6 degrees. Folding the data, absolute value of latitude, absolute value of VLSR, we get this kind of synoptic picture of the hydrogen clouds. And again, I have the UV data here in diamonds within the Fermi bubbles. The greatest LSR velocities observed are at positive velocities and at high latitude. This is not necessarily what you would expect, because although at the highest latitude here, 15 degrees, we see that we're more likely to project an outflow onto the positive velocity than a similar magnitude onto the negative velocity. The difference, in fact, over most of the latitudes is not that great. And in fact, the projection is most favorable at low latitudes. So we're really seeing something that conveys extra information for us. Let me go back to this slide for a second. If we remember that the maximum projection angle is always at the Fermi bubble walls, then what we can do is take a position. We have a latitude and a longitude of a cloud, and we don't know where it is along our line of sight. But we do know if it's positive, it's out here. If it's negative velocity, it's out here. So let's place the cloud at the Fermi bubble walls. In this case, it is the most favorable projection, and that gives us an absolute minimum on the value of the outflow velocity at that position. When we do that, and again, I'm showing here that it's not very sensitive to the exact location. We get very similar projection angles over a large distance here. When we do that, here's what we derive. This is distance from the galactic center to the cloud placed in the wall and the minimum outflow velocity that implies. And we can see right away that two things. The survey limit for clouds on the near side of the Fermi bubbles, that latitude corresponds to a survey limit here given just under 3.5 kiloparsecs. And we see negative velocity clouds, that is on the near side of the Fermi bubbles, out to the limit. We have not found the limit of this population of clouds on the near side of the Fermi bubbles. On the far side of the Fermi bubbles, however, we can see that we have a lot of space which we have probed, but which contain no neutral clouds. So a little bit over 4 kiloparsecs from the galactic center, we have run out of neutral clouds. There's some ionized gas out there, but this is largely a region where we could have detected clouds, but we didn't. And also, the minimum outflow velocity is reasonably well bounded by this diagonal line that goes up to 500 kilometers a second, 4 kiloparsecs from the galactic center. Beyond that, we really don't have any information, but for the model I'll talk about today, we just assume it's constant at 500 kilometers a second beyond that point. So we can then use this model for the outflow and for each observed cloud derive a location within the Fermi bubble. First conclusions. The data are consistent with a simple model of filled bicones, similar kinematics for H1s and the high ions, and the outflow must reach about 500 kilometers a second, 4 kiloparsecs from the galactic center. Here's a model where we just simulate the kinematics of a population which has this kind of outflow velocity. Here I'm showing the longitude and latitude. And now we can compare that to the data. Here's the data on the left, latitude, velocity, and this model, which fills our Fermi bubble cones with clouds with a similar outflow velocity that we derived. And you see right away there's a problem with it. The blue stars look kind of okay. That's clouds on the near side of the Fermi bubbles, but there's too many clouds on the too many red clouds on the far side of the Fermi bubbles. I've just enclosed a place in oval where you really see the discrepancy is very severe. What does this mean? The discrepancy shows up simply in the number of clouds as a function of VLSR velocity, which we see on the left, and those predicted by this model. There's just too many clouds predicted by the model at positive velocities. These are the most distant clouds, and what it means is that we probably have a very distant dependent sensitivity in our surveys. If we look down on this model from above, X coordinate, Y coordinate, we can see the geometry of the Fermi bubbles and why this is so peculiar. The blue clouds on the near side of the Fermi bubbles occupy just a smaller volume of space. There's just less volume available to have approaching clouds. The open circles show clouds that would be within our velocity range, which we are not considering, of 130. And then the positive velocity redshifted clouds are just have a bigger volume available to occupy, so that we really should expect to see many more of them than we do. This shows up in the derived cloud locations. Again, I outline areas. See, now on the right, it shows the cloud locations just available from geometry. That's what we could have detected clouds at those locations, those distances from the galactic center. And on the left, we see that we are just not detecting clouds there. The same thing with clouds distance from the galactic center, galactic plane, I'm sorry. We could detect clouds in theory out to about 3 kiloparsecs, and in fact, we don't see those. So what the summary is that we have two regions, one of which outlined in yellow here is a place where we believe we see clouds filling the Fermi bubbles and expanding with a simple law that is given by the values up here. And then a region where we could see the clouds and we just do not. For some reason, the cloud population ends a few kiloparsecs from the galactic center, a bit over 4 kiloparsecs from the galactic plane, a bit over 4 kiloparsecs from the galactic center. So here are my conclusions. The data in this new sample is consistent with a simple model of expansion into filled bicones with similar kinematics for H1 and the high ions. The outflow must reach 500 kilometers a second at a distance of 4 kiloparsecs from the galactic plane. We believe it's accelerating from less than 200 kilometers a second to 2 kiloparsecs. And if you just divide the average speed by a distance, it implies lifetimes of 5 million years or more. Outflow velocities in H1 of 1,000 kilometers a second seem unlikely. We see no evidence for that. Now, the model, of course, is that these H1 clouds are being accelerated by a much faster wind, and we can put no limits on that particular wind. Cloud destruction with distance. Population decreases more than 2.5 kiloparsecs from the galactic center. We could be detecting clouds out there, and we do not. And finally, the results are consistent with other evidence. A few weeks ago, Bordelais presented results from a survey up around 25 degrees latitude, showing only clouds at negative velocities. We now have considerable evidence on the cloud content in molecules and high-resolution H1 from Di Teodoro and Nunes surveys, and there's evidence of cloud evolution with distance from the galactic center. Let me end by saying that this evidence and the investigations are ongoing, not only with the GBT and ATCA and Hubble, which is the data I presented here, but APEX studies of molecular clouds in the nuclear wind, MeerKAT maps of H1 in the nuclear wind. We've just published a paper on molecules in these clouds using the LMT, and I hope that we have some data from IRAM coming before long. Thanks very much.
Thank you very much, Jay, for a great talk. We remind the participants to go ahead and put in their questions in the Q&A box. And we do have our first question. Can you see these clouds in H alpha and beta, H beta?
Not directly. There is some claim of an H alpha detection of gas in the Fermi bubbles that would be a little higher latitude and a little higher longitude, but the extinction is so large that that's really an uphill battle to see those lines.
Okay, another question. If the Fermi bubbles are remnants from a previous AGN jet, could the asymmetry be due to the central supermassive black hole magnetic poles at an angle to the plane of the galactic rotation?
Yes. We really don't have any way right now of distinguishing between cloud evaporation and a cessation of the engine, of the central engine. And so it may be, I hope as we understand the sensitivity limits of the surveys better, we'll be able to answer the question of whether it is really the cloud morphology and structure that is changing with distance from the galactic center, or the actual number of clouds. That I hope is something we can tackle before long.
Okay, a question may be connected here. Does the H1 velocity dispersion vary with distance in your measurements?
Some of the best data on this come from high resolution maps of some of these clouds in the Noon et al. Reference, which came out last year, I believe, where there are MeerKAT maps showing a very distinct change in morphology of H1 with distance from the galactic center. Now, the numbers involved, the number of clouds is small right now. We're pursuing that further, but that's a very fruitful line of research. And for now, it does appear to be consistent with an evolution of the clouds rather than a change of number caused by a change in the central engine.
Okay. Does the outflow arise from star formation or AGN activity?
I don't believe we can make that distinction.
That is fair. Those of you us who went to the Fermi Bubble conference, there's lots of discussion on that. Okay, are there any additional questions there right now? There are no open questions. I will stall for a little bit of time and thank Jay again for presenting his results. And given no more questions, well, we just have one come in just under the wire. Okay, this is one asking about the plot showing model clouds projected onto the XY plane seem to extend to positive X more than negative X. If you cut off the cloud distribution in the model at some cylindrical radius, would that not also produce the required cutoff of positive velocity clouds?
I think it's this that you're referring to, and these clouds are bound by the Fermi bubble boundaries. And so, yes, you certainly could, and in fact, that's a bit of what is implied in this figure, where we see that the empty spot on the right around 2 kiloparsecs in X and about 2 kiloparsecs in Y. That could be, I mean, that's implied that that region is empty of these hydrogen clouds. So it could be a difference in structure. Now, as we extend our H1 surveys to higher latitudes, which we hope to do, we will be filling in more of that region to the left of the empty region. And then we will be able to answer more questions about whether this is a general phenomenon or some local structure within the Fermi bubble.
Okay. Another question came in. Why is it thought that the Fermi bubbles are filled with a multi-million degree gas, as you said at the beginning?
Um, Partly it is estimates of what's needed to inflate such large bubbles and give them their properties in the X-ray and the gamma ray, but also the ultraviolet spectroscopy and those two lines of sight shows truly enormous range of ionization conditions, temperatures, and densities, uh, um, and certainly filling the region between the walls, at least kinematically, that suggests that the gas there has multi-phase. It's a multi-phase medium consisting of very hot and also very cold material.
Okay, another question on orientation. Could the tilt of the Fermi bubble explain the difference in the observed VLSR distribution?
Yeah, that's an interesting question. And what we see in our data, just looking face on with those clouds, is that there doesn't seem to be any pronounced tilt. There may be some slight asymmetries. I'll go back to this a little bit. Um, there's a, and so here we see a gap down here. Okay, is that significant? I don't know. Below the plane, we kind of fill in the survey region. So unless the sun is in a peculiar position, our starting view was that it's circularly symmetric. That, of course, may not be true in detail, and that may come out of further investigation.
Okay. A follow-up in terms of the temperature, noting that the UV lines only go up to a few hundred K.
Yeah, that's correct. Yeah, the inference on hotter material comes from X-ray studies.
Mhm. Additional question, have any observations of FRB along the axis of the Fermi bubble indicate a dispersion anomalies of electron density?
I would really love to see those data. I don't think there's enough now, but eventually, as we build up our catalogs of Fermi bubble, of FRBs across the sky, I really do hope that those will be a useful probe of the electron content of the Fermi bubbles.
Yeah, that was Another question. Are there any views as to why there is the absence of the red bubbles? Is it a measurement limitation or due to a physical difference?
It is not a measurement limitation. We have just the sensitivity for positive velocities as negative velocities in these spectra. And you can see right here in this figure, just above 10 degrees or so, 11 degrees, we just do not detect any positive velocity emission, whereas we continue detecting negative velocity emission up to the limits of the survey. And that fits perfectly with the geometric understanding that these positive velocities come from much higher up and further in the Fermi bubble.
Okay, I think we've closed out all our questions. I'd like to thank Jay again and remind everybody our next community Zoom will be in 2 weeks, August 13th. Steve Croft from UC Berkeley, Oxford, and the SETI Institute will be giving updates on the breakthrough listen techno-signature search. So thank you, everybody, and have a good day. And remember to get your NRAO GBO proposals in before 5 o'clock Eastern. Goodbye.